This is video 3 from Unit 2, Part 2, Lecture PowerPoint Notes. In this video, we are going to take a look at temperature and the specific heats to evaluate the flow of heat energy in matter. Remember when we mentioned a little while ago that to raise the temperature of water requires 1 calorie, right? To raise the temperature of 1 gram of water requires 1 calorie. The specific heat of a substance is the amount of energy that raises the temperature of exactly 1 gram of a substance by 1 degree, right? And it's different for each substance. Now, we mentioned that water, that 1 calorie is the amount of energy that is needed to raise the temperature of water by 1 degree. Now notice that there's a change in temperature, right? 1 degree. That is equal to the change in temperature. So the specific heat is the heat divided by the mass of the substance times the change in temperature. And that heat can either be calories or joules. When we're looking at the specific heat of water, that's equal to 1 calorie. Do you remember that 1 calorie is equal to 4.184 joules, right? So the specific heat of water is also 4.184 joules per gram degree Celsius. So joules is the unit in the SI system, and here's the unit in the metric system. Calories per gram degree Celsius, or joules per gram degree Celsius. Remember we talked about that metal spoon versus the wooden spoon? Well, the metal spoon gets hotter a smaller input of energy. That means it has a smaller specific heat. Let's take a look. Notice that these substances have different specific heats. Which one of them requires the most amount of energy to raise the temperature by 1 degree? Water. That means that it takes a lot more energy to raise the temperature of water by 1 degree than, let's say, gold or mercury, right? You only need a small amount of energy to raise the temperature by 1 degree. Here you go here. Here are some clickable links that you can use to help you learn more about specific heat. So, calculations using the specific heat. You are going to use these calculations to take a look at changes in temperature of a substance at 1 physical state. So let's say changing the temperature of a solid by a certain amount of energy, or a liquid, or a gas, right? It involves no state change, no change in the state. We're only talking about looking at differences in energy or temperature of substances that are either a liquid, a solid, or a gas. And this will become apparent why we say that when we take a look at heating and cooling curves. So we know that we can calculate the heat lost or gained by measuring the mass and the temperature change. So the heat is equal to the mass of the substance times the temperature change times the specific heat. So what is our formula? Q is the amount of energy, M is the mass, C represents the specific heat, and delta is the change in T, temperature, change in temperature, right? Q can either be joules or calories, okay? Remember, joules is going to be the SI, whereas calories is going to be the metric. So the amount of heat is equal to MC delta T, right? And we're only going to use this when we're taking a look at changing the temperature of something at 1 physical state, not like going from a liquid to a gas, right? So there are some things to know. The delta T is equal to the final temperature minus the initial temperature. And when calculating delta T, you're always going to use the sig fig rules for addition and subtraction. Now, if the value of Q that you get from your equation is a negative value, that means that energy is released. One thing to note, that there's no negative energy. The negative sign simply tells us that energy has been released. And what does this mean? That means that my delta T is negative. Why? Because the final temperature is going to be lower than the initial temperature, meaning that the temperature goes down and we have a negative Q. Q can be written as capital or lowercase, meaning that energy is released. If we have a positive value for Q, that means that the energy is absorbed. So that means that the final temperature is greater than the initial temperature, and that means that the temperature has increased, and we have a positive value for Q. Now, remember, the positive value means that energy is released. A negative value for Q means that a positive value for Q means that energy is absorbed, and a negative value for Q means that the energy has been released, right? Negative Q, temperature goes down. Delta T is negative. Positive Q, temperature goes up. Delta T is positive. Let's do some practice. Taking a bath might use about 95 kilograms of water. How much energy in calories and joules is needed to heat the water from a cold 15 degrees Celsius to a warm 40 point Celsius? Notice that 40 point represents two significant figures because we've got that decimal place. Now, notice this question said to heat the water from 15 to 40 degrees. Above 0 degrees, water is going to be liquid. And as long as it's below 100 degrees, water is going to be a liquid. So we know here that we're talking about one physical state. What do we have that's given? We are given 95 kilograms of water. Well, if you remember the Q is equal to MC delta T equation, the specific heat, the unit, is always in grams. So we cannot use the specific heat or the Q is equal to MC delta T equation using kilograms. We have to convert that kilograms to grams. Do you remember what I showed you on one of the earlier videos on how to convert between kilograms and grams? You're really just going to move the decimal place over 3 spaces to the right. 1, 2, 3, because it's 95 times 1,000. That means I'm going to have 3 zeros on the end, and I have 95,000 grams. Now, before we can begin our calculation, we have to do our delta T. So our final temperature is 40 degrees, and our initial temperature is 15 degrees. Delta T is equal to T final minus T initial. So 40 degrees minus 15 degrees is going to give us 25 degrees Celsius. Okay, remember we have that decimal place, and so our temperature is going to be 2 significant figures, right? So we need the amount of energy in calories and joules. Q is equal to MC delta T. Now, since we're talking about water, C is the specific heat of water, which is 1.00 calories per gram degrees Celsius. Notice that we've got Celsius, we've got grams, and we're going to find out calories by using our equation here. C is also 4.184 joules per gram degrees Celsius for water. You would be given these values. You don't memorize specific heats for substances. So first, let's do Q in joules. 95,000 grams times 4.184 joules grams degrees Celsius times 25 degrees Celsius. Our grams cancel out, our Celsius cancel out, and we're left with 993,700 joules. Well, if we're looking at, these are all multiplication, right? So I have 2 sig figs and 2 sig figs. My final answer should be 2 sig figs. And I'm going to write that in scientific notation to get rid of all of these extra spaces, right? So if I start here, 1, 2, 3, 4, 5. Oh, wait. 1, 2, 3, 4, want 5. That should actually be 5, not 10 to the 6. I'll be sure to correct the answer sheet for you. That should be 10 to the 6 joules. We can, instead of calculating directly the amount in calories, we can convert between joules to calories. And how would we do that? The number of calories would be, 9.9 times 10 to the 5 times our conversion unit, 1 calorie divided by 4.184 joules. And that's going to give us 2,366,156. And we move the decimal place over 1, 2, 3, 4, 5, 6 spaces. Our coefficient gets smaller, so our power of 10 is going to be 6, and it's going to be positive. And because there's a 6 next to the 3, we round up to 2.4. So we end up with 2.4 times 10 to the 6. Or we can do the whole entire equation, right? Where we look at what is the energy in calories. That would be 95,000 grams times 1 calorie per gram degree Celsius times 25 degrees Celsius. And we get 237,005. Was it 2,375,000? Notice that even though we have different values here, when we're rounding off to the correct number of significant figures, our answer remains the same. And remember up here, this is times 10 to the 5. One thing to note about this equation is that we can rearrange this equation to calculate the mass if we're given the amount of energy and the change in temperature. We can rearrange this equation to calculate the mass of a substance if we're given the amount of energy that was either released or absorbed and the change in temperature. Always, you're going to have to be given the specific heat. You can also rearrange this equation to determine the change in temperature. You can even rearrange this equation to determine what the final or the initial temperature is. Please be sure to watch the videos in the workshop videos for rearranging equations, which was for workshop 1, to see how to rearrange an equation and find the final or initial temperature using the specific heat equation.